X variables are correlated. They don't have to be correlated completely. They could be positively or negatively correlated, but they do share some of the information. So let's look at the first one. All VIFs were 1. Remember, a VIF, if you go back to that formula, a VIF of 1 means there is no correlation. So if all of the VIFs, variance inflation factors, are 1, then there's no collinearity. Pretty clear. How about the underlying? Let's look at the ones that are wrong, the wrong answers. The underlying model errors are autocorrelated. This is a violation of the SRM assumption that errors are independent. And this is not an indication of a problem of collinearity. How about the correlation between y and an explanatory variable is less than 0.9? Well, remember that the correlation between x and y is the basis for a model. It's necessary for a model. And collinearity, I'll never learn how to spell collinearity, 1 L or 2, only occurs, or it only concerns X variables. How about D? The observations lack constant variance. Again, this is a violation of SRM assumptions that allow us to do statistical evaluation. And collinearity can be there whether you have heteroscedasticity or you have constant variance. And how about all predictions are interpolations? This is, I mean, it's really unrelated, right? The fact that, well, the idea here is that if you are doing a prediction using your model, it's best if you only work in the range of X. That would be interpolating values in X. If you go outside of the range of the actual X data you have, you would be extrapolating your model beyond beyond the information you have. And so all predictions are not necessarily interpolations, but for the best use of a model in prediction, you should be working within the range of your X data, because anything beyond that becomes a little bit unreliable. Collinearity is not at all related. Next one that we want to cover here is question number 6. In order to check the statistical significance of the effect of adding a categorical explanatory variable with 2 categories to a regression model, it is necessary to check what? How about A? The R-squared is increased by more than 0.05. And we're trying to test for the statistical significance of a new categorical variable. Well, we know that R-squared is going to increase when you add a new variable, even if that variable is not significant. How about B? The p-value of the t-test for this explanatory variable is less than 0.05. Yes, that would be a good way of checking. Two categories, we can do a t-test for the whole thing. And so if a p is less than 0.05, then yes. For um, um, the p-test, the t-test does um, tell us that this single categorical with two states is a valid one. But remember, for a categorical for more than two states, you will need to check the partial F test, to look at all of the states combined. So yes, that is the correct answer. How about C? Why is that one incorrect? None of the t-stats in the regression model are statistically significant. If none of the variables is significant, there's a good chance that the whole model is no good. And not just the one. Check the whole F. How about D? The overall F ratio of the fitted model decreased. So if the F decreases, it means the model is less significant as a whole. It doesn't tell you about the significance of the one variable you've added or taken out. How about E? The RMSE of the fitted model decreased. Well, RMSE is a measure of the variation, of the standard deviation of the residuals. It is not a test of significance. Now, it may be a measure that's a contribution to the calculation of significance, but by itself, it is not. Okay, how about question 8? If the slope of the explanatory variable x2 in a multiple regression depends upon the level of a categorical variable that is an explanatory variable in the fitted model, then what happens? So we're looking at the slope and figuring out whether it is dependent upon a categorical variable, which level of categorical we have. And this tells me this is an interaction. So let's look at the possible answers here. The two explanatory variables must be collinear. Collinear means they are correlated, so they tend to move together somewhat. Depends, the word depends, implies an interaction. So it's the slope is changing. The slope of one variable is changing. If that variable is collinear with another, the slope doesn't change because the other one changes. But if the slope is changing due to a categorical variable, that's an interaction between the categorical and the continuous variable, not a measure of collinearity. How about B? The underlying model errors satisfy the assumption of independence. That's one of the assumptions of a simple model. but unfortunately it's unrelated to interaction between variables. Different topic. How about C? The fitted model requires a transformation so that the model is linear. Well, the model is still linear with an interaction. You know, we tend to think of these two variables being multiplied together. If you went through OIDD, you say, okay, that's a nonlinear model. But the effect here of a categorical is not to make it nonlinear, but to shift the linear model in some way, either in a parallel way with an intercept categorical, or rotating the model, rotating the line with an interaction term. So the model is still linear. It's just changing the slope. How about D? It's a slope. Uh, it depends upon the level of a categorical variable. Then this would be captured by including an interaction between x2 and the categorical variable in the model. Yes, this is, of course, the right answer. A cross product term would be needed, or an interaction term. So that is the correct answer. How about E? The categorical variable should be removed from the fitted model to reduce autocorrelation. Don't remove it. It's an important thing if there's an interaction. And unrelated to autocorrelation is correlation to itself. Again, irrelevant to this particular question. Question 10. If the coefficient of one of the categories of a three-level categorical variable in a multiple regression is not statistically significant, so coefficient of a three-level categorical and it's not statistically significant, then what? And that is t-stat is less than 2, right? So is the difference between the population mean response for that group and the overall population mean of Y is 0. So for the whole group, we can't say it's exactly 0. But we can't necessarily reject the null. So it's not exactly 0, so we'll throw that answer away. How about rows corresponding to this category should be removed? Yike. Should we ever remove a group of data? Based on its value? Essentially, you are violating the randomness of a sample. In order to do a proper sample, we need to have a random sample. That is, there's no dependence upon the data itself for the data points that we choose. If you did this based on the value of some of the X characteristics, we'd be violating that horribly. How about C? You should do nothing before looking at the effect test for the categorical variable. Yes, that is correct. Look at the partial F. That is the effect test for that variable, for that categorical variable with all of its levels. So that is the correct answer there. How about D? Why is that wrong? You should add an interaction between that explanatory variable and the response. This is saying X times Y. This now becomes a nonlinear model. So something like Y equals B0 plus B1 times X times Y. That's clearly nonlinear. How about E? You should include more observations in this specific group in the analysis. Well, this one also violates the requirement for a random sample. Just like B. Okay, those were pretty simple. Let's move on to some of the more complex questions. And we now have a group of questions that are based on a particular model. And this one is about a company that obtains its business through the use of independent sales organizations, ISOs, and wants to identify if some of them are associated with better performing advances. That is, if they bring in better business. There are three main ISOs, A, B, and C, and all of the others are grouped into a category called Other. And here we have a couple of pages of output from a multiple regression that includes the ISO variable. So what we have here is we have a 4-level ISO categorical. We have a bunch of stuff here. Something I noticed. I recommend when you do the final and you get one of these sets of questions about a model, don't start answering all the questions right away. Look at the model tables that you have and see if you notice anything that stands out. One thing I notice here is R squared is low. But even so, it may have some use. Depends. Obviously, we've not captured all of the characteristics, all of the explanatory variables that explain the how well the business is doing. Okay, analysis of variance. Let's take a look at some things. We have an F ratio of 5, and we have a p-value much less than 0.05. So this is a significant model as a whole. Good. All the rest kind of looks pretty standard. RMSE at 0.389985. That's a little bit big compared with the mean of the response, but of course that's why we have R squared being so low. We've got a lot of residual variation. Let's look at the effects tests. We have two variables. We have years in business, which is a continuous variable, and we have ISO, which is a categorical. Now we have a partial F for each of these. And of course, the probabilities say both are significant. And then if we look at the expanded estimates, that is, we've taken ISO and we have expanded it into the 4 states, and now we have estimates for each of those 4s. In other words, the amount of parallel movement or vertical intercept movement for each of those states. And notice that we've got a couple that have t ratios of less than 2. And so you have to ask yourself, is that significant? And of course, you will go and look at the overall partial F test for that variable as a whole. And yes, it is significant. And you don't want to throw that one out, even though some of the levels have a t value less than 2. Okay, so that's information that we have. We'll probably use that for answering some of these questions. So let's take a look. Based on the fitted model, the company should conclude the expected performance of a 4-year-old small business is what? So what are we doing here? We're taking a look at a example small business, 4 years old. So how about A? Is it not statistically significantly different among these ISOs? In other words, if we have a 4-year-old company, does it matter whether it's an A, B, C, or an other? And since we looked at the F stat, the partial F, for ISO, it is good. And therefore it is significant. So the impact of the type of ISO is significant. So A is not a correct answer. How about the expected performance is better or best for ISO A? Well, now we're going to have to look at the actual coefficients there. And if we look at ISO A, it's negative 0.0286 compared with B, positive 0.18, ISO C, negative 0.01, ISO other 0.026. Well, clearly, with a negative coefficient, that means it is worse performance. And in fact, it's the worst one. So B can't be correct. How about C? Best for ISO other. Well, we can look at that as well, and we see that ISO other has the largest positive that shifts the response up. So that is correct. And I want to point out something here. It's important that we identify the other variable. We hold that constant. So for example, if we were to take and try to compare 2 different companies, but they also varied in age, years in business, then we wouldn't know what the impact was of the age versus the categorical, the type of business. So we can't compare them that way. How about D? Is it worse for ISO B? Well, B is actually second best. So the coefficient for B is positive, so it's good, and it's not quite as positive as ISO other, but it's second, so second best. How about D, E, negative for some ISOs and positive for others? Well, the performance can't be negative. The performance metric is always positive. And we can prove that to ourselves by looking at the intercept. The intercept is 0.87. So no matter which type of business we have, A, B, C, or other, the impact of that will never shift that intercept below zero. So it can't be negative for some business types and positive for others. How about 20? The difference in performance in an advance originating from ISO other as compared to ISO A is, on average, what? What are these numbers are? What are these numbers? This one, if you look at it, is ISO other minus ISO A. Okay. How about B? B is the intercept of the model. How about C? C is 2 times this difference between ISO other and ISO A. And this D is the ISO other coefficient. All of these are kind of interesting numbers, right? The first one you'd think, okay, the difference in performance in an advance originating from ISO others compared to one coming from ISO A is on average 0.055, the difference in those coefficients maybe. Would that make sense? Well, the problem is you can't compare a data value from ISO other with one from ISO A to see the difference based on that type of business without also holding constant the years in business, because the difference in performance is going to depend not only on the type of business but also the years in performance. So if you're comparing two values that are two companies that have different years in business, you're going to see a difference that's due not only to the the type of company, but also the years in business. So essentially, you're saying you can't compare these two arbitrarily. You have to control the other variable. So performance also depends on years in business. So E is the only reliable answer. A would be okay if comparing companies of the same age. Very subtle, but important. When compared to advances that came through ISO other and are for 1-year-old companies, advances that came through ISO A, again, for 1-year-old companies, can expect on average to have a performance ratio of what? Okay, so now we are comparing companies of similar age, so we can look at the two. So, so years is fixed. So we can compare. So first thing we notice is that the coefficient is more than A, the coefficient for A. So A is minus 0.02, other is 0.026. So ISO other is going to have a higher performance than ISO A for the same age. So the question is, advances that came through A can expect on average to have a performance ratio more or less. And since more than A, so A is less, has lower performance than other. So we can cross out two of these. And now we only have 3 to consider. And so we've got, let's look at the difference and see what the value should be, the difference in performance. 0.0264 for other. And we're going to subtract off minus 0.0287 for A. And so the difference is 0.05512, and that happens to correspond to the number in B, and so that one is the correct. So essentially, A performance is less by 0.05512 for a 1-year-old company. Remember, you can compare them only if you hold the other variable the same. How about 20? This model predicts the average performance of an advance that came through ISO B and that was for a 10-year-old company to be what? Well, we can clearly calculate the right answer here. Calculate using the model. And so performance equals the intercept, 0.8714, plus the coefficient of years, 002, times the number of years, which is 10. So this is the intercept. This is the coefficient of years. And then we'll add to that the effect of ISO B, pulls the whole regression model up by 0.01825. If we plug all that stuff in our calculator, we get 0.909778, and that says that answer A is correct. I like those. We don't have to consider the others if we know how to do the calculation correctly. Okay, question 23. Based on the fitted model and given the multiple regression assumptions hold true, the chance that the performance ratio of an individual advance that came through ISO B is more than 0.8 higher than the predicted value in question 22 is approximately what? Well, this is a little bit complicated, right? So we're talking about a probability that ISO came through B is more than 0.8 higher than the predicted value in question 22. Remember, we predicted 0.909778 predicted. And so what's the probability that the actual is 0.8 plus that? So let's see, be 0.8, sorry, 1.709778 or more. So what are we doing? The word predicted should tell you something, right? If this is our model, and that model is for an ISO-B, we can look at a prediction interval. And we know our regression assumptions are true, so we know we have a constant RMSE, and that prediction interval is +2 RMSE above the regression to -2 RMSE below the regression. And this is for a 10-year-old ISO-B. And so that particular Y value is about 0.09. And then our prediction interval for 95% confidence is what? Well, we're going to use RMSE to calculate that interval. And that's RMSE value is 0.389985. We'll round it off to 0.4. And so 2 RMSE is 0.8. Very coincidentally, that is the actual number that we're asking to look at here. So this would be 1.7. So what's the probability that an advance 10-year-old coming through ISO-B would be more than 0.8 higher? So it would be above that prediction interval on the positive side. Well, we know that prediction interval is 95%. Below it would be 2.5%, and above it would be 2.5%, or 0.025. So 2.5 above, 2.5 below. So what's the right answer? D. We can calculate that one. Another one easy to get. Next question. The plot of the residuals shown below indicates what? And we got a box plot of all the residuals for each of the states of that ISO categorical variable. So what's going on here? How about A? Does this plot indicate that the fitted model violates the assumption of independence among the groups? Well, categorical is mutually exclusive. It can only be one of those things. So by definition, the states are independent. So that can't be the correct answer. How about B? The fitted model omits an important underlying variable. that interacts with these two variables. This information, this plot, doesn't say anything about the other variables. How about C? The error variance is similar for the different ISOs. Yes, I'd say this is correct. So basically looking at this, the vertical extent of the dots here are pretty much the same for all of these, even though there's different quantity for the different states. You can see that there are a lot more A's than there are others, for example, or C's, but the extent, the distribution is about the same. So the variance is the same. So I would say C is the correct answer, but let's look at D, make sure that one isn't. How about the underlying model errors are not normally distributed? Well, this chart is not a good choice for testing normality. I mean, you can kind of look at it. Does the concentration heavier in the middle? But really, it doesn't. You'd have to take a big leap of faith. How about E? Residuals are unreliable due to their clustering around zero. Well, residuals are unreliable. The residuals should be clustered around zero. We want, in order to have a good model, we want normally distributed residuals with a mean of zero. So we want residuals that are clustered around zero. So that's what we do want. Okay, how about 25? Is there any evidence that the inclusion of the ISO variable has significantly improved the fit of the model? So question A, yes, because R squared has increased. Well, R squared increases, but we don't know. I mean, it increases no matter what you put in, as long as it's a new variable, whether it's significant or not. So it will increase, but is it significant? We don't know. We can't measure significance with R squared. How about B? Yes, because RMSE has decreased. Again, same idea. We can't measure significance just based on the fact that RMSE has decreased. How about C? Yes, because the effect test for ISO is significant. This one sounds much better. We need a test. We need a proper test to determine significance. And so we have a partial F test that we can look at. And we have an F value of 4.26 and a P value for that of 0.0052. And that tells me, yes, it is significant. And that is the correct answer. Let's look at D, see why it's not. It says potential correlation between ISO and years in business invalidates the question. Okay, this would be a collinearity. It doesn't invalidate the question. It can still be significant. How about E? No, because some of the ISO coefficients are not statistically significant. For a multi-level categorical, you must look at the variable as a whole. You can't take part of a variable. You have to look at the whole thing. And the only way to do that, to judge its significance, is to look at the partial F test. Okay, let's see. Last time we looked at statistics, we did 26 through 23, so let's not waste any time doing them again. We did 26 through 33, I'm sorry. 33, we did that one. Okay, so now we have a new group of questions based on a new model. And so the cash advance company referred to in earlier questions has become interested in how the size of the cash advance is related to the legal status of the entity taking the advance, so the customer. The entity is coded as a 4-level categorical: corporation, limited liability, LLC, partnership, and sole proprietorship. It seems reasonable that companies with higher cash flows will take out larger advances, so they have controlled for this by including as an X variable monthly revenues, which measures exactly what it says. Below is the output from a multiple regression of advance size against entity type and monthly revenues. An interaction is included in the model. So advance size is Y, this one is X, and this is X, and this is a categorical. And they've included an interaction term. So we can look at this, and this is a continuous. This is the effect of the categorical. It's an intercept categorical. So it moves the regression in a parallel fashion. And these 4 are the interaction terms. And they are slope, they impact the slope of the model, changing the slope of monthly revs or monthly revs to be larger or smaller. What do we have next? Page has some stats, summary of fit. Oh, look at this. We've got an 85% explanation, so that's very good. What do we have here for the model? We, as a whole, the whole F test is excellent. Says very significant. And then we've got partial Fs for the 2 variables, and both of those look really good as well. So we'll take them. Now we've got some more interesting stuff as well. We've got a single effect leverage plot. Gives us leverage on the x-axis and advance size, leverage residuals. And so what are we noticing here? I'm seeing that we've got what looks to be like a heteroscedasticity issue, and we've got a couple of things here which have high leverage. Okay, how about the next one? What are we seeing here? We have a normal quantile plot um, for these residuals. And I'm going to say it's very long-tailed, not normal. Could be an issue. How about a residual plot? Okay, residual versus the predicted y. So x-axis is the predicted advance size, and the y-axis is the residual values. And again, here we see even more clearly, we have heteroscedasticity, non-constant variance. It means our prediction interval would be way off if we tried to use the overall RMSE to figure that out. Okay, clearly we're going to have some questions about that. Using the model as provided, which of the following is the expected loan size for a partnership with 50,000 in monthly revenues? So we know that the size, not sign, the size of the loan is a function of revenue and type. Okay, so we can actually plug the numbers into the model, and we have the intercept 3850. Again, I'm going back to the table of estimates here, and I can add to that the revenues, the coefficient of 0.76 times 50,000. That's what the question is asking about. So that's the revenues, plus 2027.6. This is because it is a partnership, and that is the intercept coefficient for a partnership. And then we will subtract off the coefficient for the interaction term of minus 0.164 times the monthly revenues. And add all this stuff up, we get a value of 35,766, and that happens to correspond to answer A. Again, just need to calculate the right answer. All of these numbers come from the estimates table. So we're going to choose partnership. It's this one. The intercept was here. The monthly revenues coefficient here, the slope of that, and then the interaction with partnership is minus 0.164, and the partnership parallel shift is 2027. So that's where all those numbers came from. Just put them into the model, plugged them into the calculator, and got the answer. Next one, 35. Assuming for now that the assumptions of the model hold, independence, constant variance, all that sort of stuff, is there any evidence that the relationship between entity type and the size of the advance varies with the monthly revenues? Is there an interaction? How about A? Yes, because at least one of the t-stats on the interaction term is significant. Well, we need to look at the whole variable significance. So looking at one of the t-stats is not enough. We need to look at the partial f. So looking at the t-stats, for example, we've got entity type and size of advance varies with the monthly revenues. So we've got t-stats that are less than 2 and greater than 2. But we have to look at the whole thing. We have to look at the partial F, and what we're seeing is this beautiful 50.97 F ratio. But just looking at the t-stats doesn't answer that question. How about no? Because at least one of the t-stats on the interaction term is not significant, same as A. We need to look at the whole partial F for the variable as a whole. It makes a lot of sense, right? You're going to have various levels. Some will move it up and down. Some will change the slope more or less. And you've got to have some that are at the extremes and some that are closer to zero. Otherwise, you don't have different levels. So you have to look at the effect of removing that variable from the whole model to see if it has a significant impact. How about C? Yes, because the overall ANOVA F stat is significant. So the overall F includes all variables. And does not distinguish individuals. So that's not going to be a useful measure to judge by. How about yes, D, because the effect test for the interaction term is significant. Yes, the F effect is 50.97, and the P is less than 0.0001. So that is a good answer. How about E? There's no information on the output available to answer this question. Wrong. CD. This is how you use those tables. Next one, the leverage plot for monthly revenues shows a clearly leveraged point. If this point were removed from the analysis, then which of the following would most likely occur? Leverage plot for monthly revenues. Ooh, wrong page. So that's this plot up here. Not that one, this one. And so we've got some pretty clear outliers here. We've got one way up there at the far corner. I think that's the one they're referring to. Clearly leveraged point. If this point were removed from the analysis, then which of the following would likely occur? Remember leveraged. So look at that. It's leveraged. It means it's way out on the edge of the tree limb in the x direction. So if we move that a little bit, yeah, it would have a strong effect on the slope of the line. However, it is pretty close to the line as it is. So if we just pull it out, the line wouldn't change because we pulled it out. Now, if it were influential, that is, if that outlier were way down below or above the line and we pulled that out, then the influence of that outlier would be removed and the slope of the line would be expected to change substantially because as it is, it would have pulled the whole line in one direction or the other. So let's take a look at what we have possibilities here for. So how about the standard error of the partial slope of monthly revenues would decrease. And then B, the standard error for the partial slope of monthly revenues would increase. Well, let's look at standard error. Now, partial slope, that means the influence of that variable taking into account the other variables. So that's the right thing we should be looking for. So the standard error of the slope, remember, is equal to the RMSE divided by the square root of n times 1 over standard deviation of x. So now we have a little problem because RMSE is not constant throughout the range, but let's take a look at the even more important part, and that is if we remove an outlying point, and it's outlying in x, then the standard deviation of x will decrease. Since that one point that's way out is going to add a lot to the range of x. And so because the standard error is proportional to 1 over Sx, standard deviation of x, the standard error increases. So let's see what happens. So B says the standard error for the partial slope would increase, and that's what we figured out. Let's take a look at A. Now, A says it would decrease. That's the opposite of what we concluded. And B is correct. So B is the correct answer. How about C? Why is R squared would substantially increase? R squared, of course, is 1 minus RMSE squared over S standard deviation in Y squared. RMSE doesn't change substantially. And how do we know that? Because it's not an influential point. That is, it's not above or below that line. It's on the line. We're pretty close to it. And would expect little change to the model. So it's not going to pull up or down. It's not going to affect the variation of the residuals in the y direction. How about D? RMSE would substantially increase. Same argument. Not an influential. So essentially, another way of talking about that would be that removing a point with a residual pretty close to 0 would not change RMSE. So if you remove a value of 0 from the calculation, it doesn't change much. How about the autocorrelation of the residuals would decrease? Residuals are independent. That's an assumption we have to make. That is, there's no correlation between individual residuals, and we have no pattern observable. Look at those residuals, look at those residuals. I don't see a pattern other than, of course, heteroscedasticity, but that's not a sign of autocorrelation. So B is the correct answer. The standard error for the slope of monthly revenues would increase. Next one, 37. With regard to the regression diagnostics, which of the following statements best describes the situation? Residuals are heteroscedastic. Residuals do not come from a normal distribution. Residuals are not mean zero. Both A and B are true, but all of A, B, and C are true. Well, we have some possibilities here. How about A? Are the residuals heteroscedastic? Here's the residual plot. Very clearly, the variance of the residuals changes over the range of the data. So they are heteroscedastic. And you can see this on both the leverage and residual plots. Probably the residual plot is the most reliable one. Easiest to see this. How about B? The residuals do not come from a normal distribution. Well, here we looked at the quantile plot for the residuals, and we see clearly it's long-tailed and not normal. It's concentrated in the middle. The tails go out farther than the normal. So now we've in two ways we've blown our assumptions, and we got some problems calculating RMSE and therefore calculating any of the other measures of goodness. So this one we would see the normal quantile plot, and that would tell us they are not normal. How about C? The residuals are not mean zero. Let's take a look at that quantile plot again. And yes, perfect. The residual mean right in the middle is exactly on the zero line. So that one is, come on, there we go. No. The quantile plot shows the center at zero. And so the best answer we have here is A and B are true. And then E, of course, C is not true. So here's an example of why it pays to look and read at all 5 possible answers. If you just hit A, you saw that would be true. Pick that, but more than one of those answers is correct. Okay, and finally we've got, if this model were used to create a 95% prediction interval for a corporation that has monthly revenues of 200,000, then what would happen? So we're going to try to use this model for prediction. And so we've got a corporation and we've got monthly revenues of 200,000. So we have values for the X that we could plug into the model. But here's the problem. We have heteroscedasticity. And so is the prediction interval wider than it should be? Is it narrower than it should be? The prediction interval, will it have 95% reliability by construction? Is that by definition, that's what it's going to be? How about the prediction interval will be longer than a 99% prediction interval, or we'll have a coverage rate of 84.9%. None of those two makes any sense. But what we have here is, if you look at it, this is around where the 200,000 point is. And if you look at any of the model numbers, here we go, this one, 200,000 is up here, way out where the variance of the residuals is quite big. So the red dotted lines are what would be the actual prediction interval. Since RMSE increases, so if we were to actually do a correct prediction interval, not one based on just RMSE overall, we would have one that varies over the range of revenues. The calculated one would be based on a single value of RMSE that covers all of them. That would be the yellow lines. So what we see here is the calculated prediction interval at 200,000 is narrower than it should be. And so I can pick directly answer B as the correct answer here. And this is an important one to understand. I'm fairly positive, fairly certain, have a high confidence level that you're going to see a question like this on the final exam. So understand that if you have heteroscedasticity, the prediction interval that you calculate in the normal manner, plus or minus 2 RMSE, will not be accurate for most of the range of the data. And the actual prediction interval will depend on the RMSE at any particular point, any particular place along that x-axis. And so if your heteroscedasticity increases with positive x, then your what should be the correct prediction interval becomes larger, and your calculated prediction interval at large values of x is too small, at small values of x is too large. So I think the picture here illustrates it pretty well. So that's it. That's all we have for tonight. We managed to do it in just a little over 3 hours, so that's pretty good. We didn't have to do all of the questions on this because we handled some of them last time. Hopefully this wraps up all of the topics that you've covered so far. We'll do one more statistics tutorial session, and that will be kind of putting it all together. Maybe not as important for reviewing for the final exam, but just kind of should cement the idea of how you build this model. How do you take all of this output, put it together, and use it to either predict new values or to use it to understand the impact or influence of these particular variables on something of interest. So we'll do that, and I think that's a fun one to do. Hopefully it kind of pulls everything together for people. So with that, I'll say good evening, and we'll post the recording in the comments. I'm sorry, recording as soon as it's available, and the notes right now. And hope it's been helpful for you. Thanks a lot.